Okay, this is 4.6 taking sides, and this is a practice understanding task. Okay, and so in today's activity, we're going to have Joaquin and Serena, and they're interacting about their mathematics, particularly inequalities. And, we need to understand that when we're talking about math, it's okay to disagree, and we're going to make mistakes. That's okay. That is how we learn. And Joaquin and Serena make a very good pair that can work together. And by working together, they are both becoming much better mathematicians. So let's watch what happens here. Joaquin and Serena work together productively in their math class. They both contribute their thinking, and when they disagree, they both give their reasons and decide together who is right. Remember, in math, it's okay to be wrong. In their math class right now, they are working on inequalities. Recently, they had a discussion that went something like this. Joaquin, the problem says that 6 less than a number is greater than 4. 6 less than a number is greater than 4. I think that we should just follow the words and write 6 less than a number. So Joaquin went 6 minus n is greater than 4. Okay, now 6 less than a number, okay, the number would be n. And to me, 6 minus a number does not mean 6 less than a number. So I'm questioning Joaquin. Let's see what Serena has to say. I don't think that works, because if n is 20 and you do 6 less than that, you get 20 minus 6 is 14. I think we should write n minus 6 is greater than 4. So let's see. 6 less than a number. So if my number is n, would n minus 6 be 6 less than a number? I think so. And then is greater than 6 less than a number, n minus 6 is greater than 4. Well, I have to give this one to Serena right there. So Joaquin, how's he going to respond to that? Oh, you're right. Yeah. So 6 less than a number, we'd have to write n minus 6. Okay. So let's solve Serena's inequality and see what happens. So let's take this inequality. N minus 6 is greater than 4. And this is a one-step inequality right here. We have to undo this subtraction by 6. And what's the inverse of subtracting? Let's add 6 to both sides. So n minus 6 plus 6 gives me an n on the left, so n is greater than 4 plus 6. You can combine those, and that's 10. N is greater than 10. Nice job, Serena. Okay, then it makes sense that the solution will be n is greater than 10. Hey, look at that, which means we can choose any number greater than 10. That's right, Joaquin, good job. So let's go ahead, and you know that n is greater than 10. This is called set notation right here. And we're practicing interval notation. So let's go ahead and go interval notation. If n is greater than 10, as soon as I see interval notation, I think comma. And then what is my left bound? Well, n has to be greater than 10. So my bound on the left would be a 10. And my bound on the right, well, if n is greater than 10, that means we can go on and on and on and on. And to do that, we go infinity. And can n equal 10? No, n is greater than 10. So rather than a bracket, we go parenthesis. And since we can never reach infinity, we have to go a parenthesis on the right as well. There's the interval notation. N is greater than 10. And the open interval from 10 to infinity, those two are different notations for the same thing. And you guys need to know both of them. And now let's practice graphing. Right on. So I like to just do a horizontal line. And since n is greater than 10, I only need one hash mark. And I'm going to label that hash mark with a 10. And now greater than, what is my dot? Well, n can never equal 10, so my dot has to be open. And greater than would be all of the real numbers to the right of that 10. So I'm going to go array going to the right. So the graph, the interval notation, and the set notation, these three things all say the same thing, and it's the solution to Serena's inequality. The situations below are a few more of the disagreements and questions that Joaquin and Serena have. Your job is to decide how to answer their questions, decide who is right, and give a mathematical explanation for your reasoning. Wow, we're becoming mathematicians here. So number one, Joaquin and Serena are assigned to graph the inequality x is greater than or equal to -7. Well, let's go ahead and join them in that assignment. So let's graph this inequality. Again, now you could start with just a horizontal line without hash marks and numbers, but I think this was given in your activity, so there it is. And I look, do you see the -7 is my key number right there? So I have that hash mark right there on -7, and I've got to look at this inequality now. What kind of dot? Open or close? Do you see the equal sign? That means we'll use a closed dot. Equals implies we need a closed dot. Good. Okay, now x is greater than or equal to that -7. That means we're going to have a ray going to the right, which represents all real numbers to the right of -7 and including -7. So x is greater than or equal to -7 right there. So here we go. Let's see what Joaquin thinks. Joaquin thinks the graph should have an open dot at -7. Now, Joaquin, if we put an open dot right there, that would mean x does not ever equal -7. And we have an equal sign right there. So, Joaquin, I can't agree with that. Serena thinks the graph should have a closed dot at -7, and we agree with that. Explain who is correct and why. So Serena is correct because x can equal -7. That equals right there. And if x can equal the number, we put a closed dot. That means in the interval notation, we'd use a bracket at the -7 too. Serena is correct because x can equal, and that should say a -7 right there. That's a typo on my part, I'm sorry. All right, number 2. Joaquin and Serena are looking at the problem 3x plus 1 is greater than 0. Well, as soon as I see an inequality, I want to solve it. So let's solve it before we look at what Serena and Joaquin did. 3x plus 1 is greater than 0. So we have to undo that plus 1 with a -1 on both sides. Bring down your inequality. And we have 3x plus 1 minus 1 is 3x. And 0 minus 1 is -1. And now you have one more step. Let's divide both sides by 3. So the 3's cancel on the left, and we have x is greater than -1/3. Great. Well, let's go and take a look at what Serena says. Serena says that the inequality is always true because multiplying a number by 3 and then adding 1 to it makes the number greater than 0. So she's just looking at this inequality right here and saying if I multiply a number by 3 and then add 1, I will be greater than 0. But when we solved this, we said, no, that's not the case because x has to be greater than -1/3. Therefore, it's not always true. And we can show that pretty easily by showing Serena a graph. So here is my number line, and I'm going to put a hash mark for -1/3. So -1/3 would be about right there. Okay, and greater than, I need an open dot. Okay, and x is greater than -1/3, so my ray will go to the right, representing all real numbers to the right of -1/3. And we do not include that -1/3 with the open dot right there. So let's look at Serena's statement again. Serena says that the inequality is always true because multiplying a number by 3 and then adding 1 to it makes the number greater than 0. Well, if it were always true, then any real number would work. That means if I throw a -3 in there, it would have to work. Well, let's take a look at that. 3 times negative 3 would be negative 9, plus 1 more would be negative 8. Is negative 8 greater than 0, Serena? It is not. So you're not correct. Okay, sorry. So, is she right? Explain why or why not. And this graph explains that Serena is not correct right there. No, x must be a number that is greater than negative 1/3. Greater than negative 1/3. Let's practice interval notation now here, because look at what we have. We have set notation right there. X is greater than negative 1/3. We have a graph that says the same thing. So let's keep practicing all of our notations. All right, interval notation, there's my comma. And x is greater than negative 1/3. So my bound on the left is that negative 1/3. All right, and I'm going forever and ever and ever to the right. That's infinity. And because of the open dot, x cannot equal negative 1/3, parenthesis, and we can never reach infinity, so parenthesis on the other side. If we could equal either of those endpoints, we'd put a bracket rather than a parenthesis. Number 3, the word problem that Joaquin and Serena are working on says 4 greater than x. 4 greater than x. Joaquin says that they should write 4 greater than x. Serena says they should write 4 plus x. So who's right, Joaquin or Serena? Now, 4 greater than x. That's great, but if I read this inequality, I would read this like this. 4 is greater than x. All right? And then look at Serena. 4 greater than x. So if I have some number x and I add 4, would that be 4 greater than that x? I'm banking on Serena right now. So explain who is correct and why. Let's justify. All right. So let's let x equal any number. How about we say x equals 2? So that 2 is now x. Now, if we go, what is 4 greater than x? That means we have to go 4 hash marks to the right of that x. 1, 2, 3, and 4. And there we are. So this 6 is actually 4 plus x. Do you agree with that? All right. So I like what you're saying, Joaquin, but you didn't quite get that translation perfectly. And Serena, you are correct again. A number 4 greater than x equals 2 would be 6. Serena has to be correct. Okay, no problem there. Okay, so let's do one more and then we'll take a little break on the video. Joaquin is thinking hard about equations and inequalities and comes up with this idea. If 45 plus 47 equals t, then t equals 45 plus 47. Can we all agree with that? So that's like saying if a equals 2, then 2 has to equal a. And you guys, that's called the commutative property right there. And that works. So when we have an equation, what we have on the left and right, we can reverse that and it's still the same equation. So 45 plus 47 equals t is the same thing as t equals 45 plus 47. So now Joaquin is thinking, I wonder if that works with inequalities. So if 45 plus 47 is less than t, then t would have to be less than 45 plus 47. Is he right? Explain why or why not. Well, let's put Joaquin's thinking on a number line. The sum of 45 and 47 is less than t. Is less than t. Number line. Okay, well, what is 45 plus 47? That would be 92. So, 92 right there. Okay, and I'm going to go is less than, all right, so less than, open dot, there's no equals, t. So this sum is less than t. That means t would have to be to the right of that. So I'm going to draw a ray from this open dot at the 92 going to the right to represent every real number to the right of 92. Okay, and there's a graph of 45 plus 47 is less than t. 92 is less than all my t's. Those are all my t's right there. Now, let's do it the other way. So literally, what does this say? T is less than the sum of 45 and 47. Okay, there's our number line again. Okay, and now the sum of 45 and 47 is still 92. Okay, open dot, there's no equal, less than. So t is less than the sum of 45 and 47. So if t is less than this number 92, wouldn't our ray be going to the left? There's all my t's there. Those are not the same graph. So this commutative property does not work for inequalities. Okay, Joaquin is, I'm sorry Joaquin, but incorrect, but you're learning. Okay, the commutative property does not apply to inequalities. All right, number 5. Joaquin's question in number 4 made Serena think about other similarities and differences in equations and inequalities. Serena wonders about the equation negative x over 3 equals 4, and the inequality negative x over 3 is greater than 4. Explain to Serena ways that solving these two problems are alike and ways that they are different. How are the solutions to the problems alike and different? Okay, well, let's solve them both then. So, there they are right there. We have negative x over 3 equals 4, and we have negative x over 3 is greater than 4 right there. Well, if we're going to solve this equation, we have to undo this division by, and you could think of this actually right now as, let's just undo the division by 3 because I'm going to make a point in a second. So can I simply multiply both sides by, and I'm going to multiply by negative 3, watch, because I'm dealing with this negative and the divisor of 3 right there. Okay, so take a peek here now, equals, all right, now the 3's cancel right there is the easiest way to see that. And what do you have? Minus a negative, and minus a negative x would be a positive x. Or you could have just thought, okay, I am multiplying by negative 3 to undo the negative and the division by 3 in one step. And then on the right, we have 4 times negative 3 is negative 12. So in the equation, x equals negative 12. So when we do the inequality, our first step is exactly the same, except what did we just do? We multiplied an inequality, both sides, by a negative number. Now remember the key rule of solving inequalities. When you multiply or divide both sides by a negative number, you must reverse the inequality or the orientation of the inequality symbol. We've got to flip that greater than. So it becomes a less than. And now your 3's cancel, and those two negatives undo each other to give us the x. X is less than. 4 times negative 3 is still negative 12. These are very different answers. In the equation, x equals the number negative 12. And in the inequality, x can be any number less than negative 12. Let's graph them both. So the inequality, x equals negative 12, that is just that point right there. Solid dot. Now look at the inequality. Same number line, but now there's no equals, so I have to put an open dot on that negative 12, like that. All right, and less than would mean that's everything to the left. Look at the difference there. So, explain to Serena ways that solving these two problems are alike. Well, we did our first step. We multiplied both sides by negative 3. And ways that they are different. But when we did that, our solutions were very different because the solution to an equation is a number, and the solution to an inequality is a set of numbers. It's an interval of numbers. Okay, so to solve the equation and the inequality, we multiply by -3. But when we multiply or divide an inequality by a negative number, we must reverse the orientation of the inequality symbol. The solution to an equation is a point. That point, in this case, -12. The solution to an inequality is an interval. This is an interval. It is all real numbers less than -12. Number 6. Joaquin solved -15q is less than or equal to 135. Now, how would you all do that? We'd have to undo that multiplication by -15. So we would divide both sides by -15. And Joaquin added 15 to each side of the inequality. Serena said that he was wrong. And we're going to have to agree with Serena. Serena is correct. Okay, you do not undo multiplication by -15 by adding 15. Okay, so Joaquin's solution was Q is less than or equal to 150. See, he added 15 to the 135. All right, and he checked his work by substituting 150 for Q in the original equation. Okay, so let's do that. So Joaquin needs to, by the way, Joaquin needs to divide by -15, not add 15. So, but when Joaquin checked his work, look what happened. -15, and what did he do? He substituted 150 for Q. So this Q right here is now 150, and Joaquin wants to know, is this a true statement? So what is -15 times 150? Well, I'm going to punch that on a calculator, but I think that's what, 2,250 negative possibly. Let's double check though. -15 times 150, and yeah, -2,250. And that is certainly less than or equal to 135. It's less than. So that's true. All right. So, and Joaquin has been trained when you solve an equation, you can substitute your solution into the original equation and see if you get a true statement. So he tried to do this with an inequality. All right. But here's the problem. This is an inequality. So there are an interval of real numbers that would be a solution to this inequality. All right. And, you could have one number that works when you plug it back in. But again, that does not mean you're correct, because the solution to an inequality is an interval of numbers. So does this prove that Joaquin is right? No, I'm sorry. This does not prove Joaquin is correct. The solution to an inequality is an interval of numbers. And in any interval of numbers, we can go back and peek right here. Look at our last graphs. If I can get there. See, this ray is an interval of numbers right there. And how many numbers are on this ray? Infinitely many. All right? There are infinite solutions to this inequality. To this equation here, there's only one solution. So where were we? So there we go, right there. This does not prove Joaquin is correct. The solution to an inequality is an interval of numbers with infinite solutions. Joaquin is still skeptical and believes he is right. That's cool. Find a number that satisfies his solution but does not satisfy the original inequality. Well, what we need to do then is solve the original inequality correctly by dividing by -15, and then let's graph it. Okay, find a number. So there it is. -15q is less than or equal to 135. And to undo this multiplication, we're going to divide by -15. All right, and remember, when we divide an inequality by a negative number, both sides, we have to reverse our orientation. So this less than or equal to is now greater than or equal to. And on the right, or on the left, excuse me, the -15's cancel. And we have q is greater than or equal to. And how many times does negative 15 go into 135? That would be negative, and let me see. Let's see if we can do this without. Would that be, I think that's a negative 9, but let's double check. 135 divided by negative 15. I didn't type that in correct. Let's try that again. 135 divided by negative 15, negative 9. Okay? And you guys remember, notice I always try to do the arithmetic in my head. But you know what? I also want you guys to double check on your calculator. Get used to your calculator. It's a great tool. All right? Because you don't want arithmetic mistakes when you're doing algebra. It's hard to get algebra correct when you're making an arithmetic mistake, so double check. So Q is greater than or equal to negative 9. Let's graph that. So there's my number line. Here's negative 9 right there. And what kind of dot? Do you see the equals? That's going to be a solid dot. And then greater than or equal to negative 9. Well, greater than would be every real number to the right of that negative 9. So let's draw our array just like that. And there's a graph of this inequality right here. All right, now let's make sure we answer the question. Joaquin is still skeptical and believes that he is right. Find a number that satisfies his solution but does not satisfy the original inequality. So all the numbers that would satisfy the original inequality are in this graph right here or in this inequality right here. Now let's pick a number not in that interval, like maybe negative 10. Let's see if this negative 10 works for Joaquin's solution, but not the correct solution. So negative 10 less than or equal to 150. Well, I agree it works there. And we could even go right here. Negative 15, the original, negative 15 times Q, which is negative 10, is less than or equal to 135. Well, negative 15 times negative 10 is 150. Is 150 less than or equal to 135? Okay, doesn't work, man. Okay, so things aren't working right there. Not equal there. All right, so Joaquin, again, this isn't working. We've got to undo multiplication by division. Okay, number 7. Serena is checking her work with Joaquin and finds that they disagree on a problem. Here's what Serena wrote. And apparently Joaquin disagrees with this. So let's take a look. Serena started with the inequality. 3x plus 3 is less than or equal to negative 2x plus 5. Now, what did she do to get to this second step right here? Well, that plus 3 is no longer on the left, so it looks to me like she subtracted 3 from both sides. 3x plus 3 minus 3 is 3x, and over here on the right, negative 2x plus 5 minus 3 would be negative 2x plus 2. So that works. Looking good so far, Joaquin. Then her next step, she is saying x is less than or equal to 2. So she must have divided by 3. So 3x divided by 3 is x is less than or equal to. But wouldn't that be negative 2x plus 2 divided by 3? I don't see how she made this jump right here. Oh, I see what's going on. She needs to add 2x to both sides to get the x's on the same side. And it looks like she subtracted the 2x's. So that step is not working. Joaquin, you're right. Let's help Serena fix this problem. And we're okay with our first step right there. So let's go ahead and start right there. This we agreed with. But right now, okay, whenever you're solving an equation or an inequality and your variable you're trying to solve for is on both sides, you need to get that variable on the same side. So Serena should have added 2x to both sides. And now 3x plus 2x, well, let's bring down our inequality. That would be 5x's, and negative 2x plus 2x is gone, leaving us the 2. And then we need to undo this multiplication with what we call the multiplicative inverse, or division. Divide both sides by 5. And now, less than or equal to, our factors of 5 cancel, and we have x is less than or equal to 2/5. All right, so Serena, you were incorrect, and this, us solving it, explained why right there. Okay, so it didn't work. Sorry, Serena. Okay. Now, number 8. Joaquin and Serena are having trouble solving -4 times 3m minus 1 is greater than or equal to 2 times the quantity m plus 3. Yeah, that's a complicated inequality right there. We have m's on both sides. We have grouping. Wow. Okay. Explain how they should solve the inequality, showing all the necessary steps and identifying the properties you would use. So what we're going to do then is we're going to show every step, and we're going to talk about what property we use to determine what step we would do each time. And this is kind of prepping you for, like, next year you're going to start doing a lot of proofs. And in a proof, you know, when you make a statement, you have to be able to justify what you did. All right? And believe it or not, when you solve an equation or an inequality, you're actually proving something. You're just not justifying every step with the properties of algebra. All right, so they're starting to get you to see that a little bit. We're not going to do a lot of that this year, but it's an introduction. So here is this beautiful inequality right here. Now, you know, usually when we have grouping symbols, we want to get rid of them if we can, and we do that with the distributive property. So why don't we distribute on both sides of this inequality, and that is nothing more than the distributive property right there. So let's distribute the -4 to the 3m, and that would be -12m, and also distribute the -4 to the -1, -4 times -1 plus 4, and then do the same thing on the right. 2 times the m is 2m, and then 2 times the 3 is 6. Now, what would you do next? Well, you still have m's on the left and m's on the right. All right? So, again, what do we want to do? You could subtract 2m from both sides or add 12m to both sides. And it doesn't matter which way you go here, all right? So, but we're adding, all right? So that's called the additive property right there. And let's see, did I add a -2m to both sides, or did I add a 12m to both sides? Because it doesn't matter. So again, I kind of like to keep things positive, so it looks like I added 12m to both sides. Okay, let's rewrite. Greater than or equal to, and -12m plus 12m is gone, leaving the 4. And on the right, 2m plus 12m, that would be 14m's, plus that 6. All right, and now we have to get rid of this plus 6 by adding -6. So we still call this the additive property. All right, let's bring down our greater than or equal to right there. And we've got 4 minus 6 is -2. And 14m plus 6 minus 6 is 14m. And now we have to undo multiplication. And you guys are great at telling me you divide to undo multiplication. And a mathematician calls that, we are undoing multiplication, we call that the multiplicative inverse. Don't stress that a lot, but that's the same thing as saying, hey, we're dividing both sides. And what are we going to divide both sides by? 14. So, greater than or equal to, because we divided by a positive number, does not reverse our orientation. And let's reduce -2 over 14. A negative over a positive is negative, and 2 over 14 would reduce to 1 over 7. So -1/7. And then on the right, the 14's cancel, leaving our m. So m is less than or equal to -1/7. Or you could read that -1/7 is greater than or equal to m. I like to read from my variable because it makes it easier for me to graph. Okay, so explain how they should solve the inequality, showing all the necessary steps and identifying the properties you would use. Great. Okay, number 9. Joaquin and Serena know that some equations are true for any value of the variable, and some equations are never true, no matter what value is chosen for the variable. They are wondering about inequalities. What could you tell them about the following inequalities? Do they have solutions? What are they? How would you graph their solutions on a number line? Okay, well, let's just go ahead and take a look at A, which is 4s plus 6 is greater than or equal to 6 plus 4s. Oh, look at, they just changed the order here. Isn't 4s plus 6 equal to 6 plus 4s? Okay, all right, so they are equal. So I'm thinking this is going to work, right? But let's solve. So you know the rule. If we have our variable on both sides, we need to get it to one side. And how would we do that? All right, by the additive property. We're going to add negative 4s to both sides. Now let's rewrite. Greater than or equal to, and 4s minus 4s is 6. And 6 plus 4s minus 4s, that gives me a 6 on that side. So my s's canceled on both sides there, and I'm left with the statement 6 is greater than or equal to 6. And that's true, because 6 equals 6. It worked. All right? So what does that mean if we solve an inequality and our variables just cancel out, leaving us a true statement? 6 is greater than or equal to 6 because 6 equals 6. So that means this. Our variable s in interval notation can be any real number. So that means my left bound is negative infinity, and I can never reach negative infinity, so parenthesis, and I can go far, far to the right, any s value I want. Positive infinity, and I can never reach positive infinity. And they wanted that in a graph too. Well, s is in, this is the set of real numbers. It's anything. So I break out my number line, and it's anything. The s's go on forever in both directions. Oh, how cool. Now, look at the next one. I have 3r on the left and 3r on the right. So, you know, depending on the 5 and the negative 2 here, let's see what happens. Let's subtract 3r. Bring down the greater than, and 3r minus 3r is gone, leaving the 5 is greater than 3r minus 3r, gone, negative 2. Is 5 greater than negative 2? Again, that's true. 5 is greater than negative 2. So now we're talking about r's, so that applies r is in, and again, this is a true statement. So our left bound is negative infinity, which we can never reach. And our right bound is infinity, which we can never reach. So again, r is in the set of real numbers. And that graph looks just like the graph above, except instead of s, now we're talking r's. All right. C. I bet you this one's not going to work because, come on, we have to have one that doesn't work. So if we're solving this, aren't we going to distribute the 4 to both terms here? So distributed property, 4 times n is 4n, and then 4 times 1 would be plus 4, and now that looks familiar. 4n plus 4 is less than 4n minus 3, and you would subtract 4n from both sides. Less than, and 4n minus 4n plus 4 is 4, and then 4n minus 3 would be negative 3. Now, is 4 less than negative 3? That is not true. Doesn't work. 4 is not less than negative 3. All right? Therefore, this implies that n is in. So this means no n's will ever work. It's the empty set. And how do you graph the empty set? There's nothing to even plot. So I'm going to leave it just like that. There are no solutions. Number 10. The partners are given the literal inequality ax plus b is greater than c to solve for x. Ax plus b is greater than c. Joaquin says that he will solve it just like in an equation, which we typically do. But then Serena says that he needs to be careful, because if a is a negative number, the solution will be different. What do you say? What are the solutions of the inequality? All right, well, let's solve and see what's going to happen here. So if I'm going to solve for this x, the first thing I'm going to do is get rid of that plus b right there. Let's subtract b from both sides. So we have a times x, and over here we cannot combine these, so that's c minus b. All right, and then Joaquin says let's divide by a. But this is an inequality, and if we multiply or divide by a negative number, don't we have to reverse the orientation of our inequality symbol right there? So we do have two possible situations here. If a is positive and we do this division, all right, boom, positive, the inequality stays the same, greater than. And the a's cancel, and we have x is greater than c minus b over a. Now, if a is negative when we do this division, all right, we divided by a negative number, so we have to flip this inequality symbol, less than, and now the a's cancel, so x is less than c minus b over a. So Serena was correct, all right. When we are solving an inequality, we have to remember the rule. Whenever we multiply or divide by a negative number, we must reverse the orientation of our inequality symbol. Wow, that's it. So let me close it then. So you guys, I hope you've had fun with these inequalities. And, you know, our job is to be able to solve an inequality, to write your solution in set notation, interval notation, or using a graph. And remember that most important rule. When you are solving an inequality, if you multiply or divide by a negative number, you must reverse the orientation of your inequality symbol. Or in layman's term, flip that inequality symbol. You all get your ready, set, go done for this section, and have a great day.